When radio frequency wireless networks face strict limitations, whether due to security requirements or electromagnetic interference rules, we rely on non-directed, non-line-of-sight infrared links. The transmitter floods the room with a broad optical beam, and the photons ricochet off the geometry of the space to reach the receiver. But relying on diffuse reflections introduces severe physical penalties. Because the photons take varying paths to the detector, the signal smears in time, a phenomenon known as multipath dispersion. Simultaneously, as the broad beam spreads and absorbs into surfaces, the signal suffers massive path loss. Then there is the external interference. The receiver operates in an environment flooded with ambient light. Solar radiation passing through windows and continuous emission from artificial lighting actively bury the intended infrared signal. All of this must be decoded by sensor nodes operating under strict physical constraints. These are miniature devices tied to finite battery capacities and driven by microcontrollers with minimal computational headroom. Achieving a highly reliable link, targeting a bit error rate below 1 in a billion, is impossible if we rely on brute force transmission power. To survive within a tight power budget, we have to engineer the physical layer of the network from the ground up. We establish our mathematical baseline by modeling the channel impulse response. This 3D wireframe utilizes a Monte Carlo ray tracing algorithm, simulating exactly how individual photons propagate from the emitter to the receiver across multiple surfaces. By applying Fong's reflection model, the algorithm calculates the exact degradation of the optical power. It isolates the high-intensity line-of-sight components and tracks the sequential energy drop of the light undergoing multiple diffuse reflections. But signal attenuation is only half the problem. To reconstruct the data, the system must overcome total noise variance, the mathematical sum of the ambient shot noise and the receiver's own thermal noise. Shot noise is a direct product of the environment. It is dictated by the spectral radiant emittance of sunlight hitting the windows, combined with the optical power spectral density of tungsten lamps positioned on the ceiling. Thermal noise, on the other hand, is generated internally. It is the unavoidable electronic friction produced by the FET-based transimpedance preamplifier sitting inside the receiver circuit. If a constrained sensor node attempts to filter this combined noise floor purely through digital processing, the compute overhead will drain its battery almost immediately. The spatial signal must be physically isolated before any digital conversion takes place. The hardware solution to this physical problem is the non-imaging angle diversity receiver. By dividing the field of view into distinct spatial branches, the node can isolate the directional signal from the ambient noise. This matrix details the 3 primary angle diversity geometries and their specific signal collection equations. First, the sectored receiver, or SDR. It maps photodetectors across a subdivided hemisphere covered by a broad, long-pass filter, resulting in wide angular coverage but high vulnerability to background light. Next is the self-orienting receiver, or SOR. It uses a single detector capped with an extremely narrow 3-degree lens. To find the signal, a digital signal processor actively calculates the optimal direction and physically steers the lens using an electromechanical mount. Finally, the conventional angle diversity receiver, or CDR. This architecture utilizes multiple separate branches, often a vertical element facing the ceiling, surrounded by several angled elements, all completely fixed in place. Inside every individual branch of the CDR, a narrow bandpass filter strips away ambient light, while a compound parabolic concentrator funnels the remaining photons. This highly specific pairing decouples high optical gain from the strict field of view restrictions that plague bare detectors. Mathematically, the CDR maximizes signal collection. It avoids the heavy power draw of the SOR's mechanical steering system while simultaneously rejecting the background noise that easily penetrates the wider sectored receiver. Capturing parallel spatial signals is only the first step. The receiver must still synthesize these separate branches into a single data stream, and the chosen algorithmic combining technique chosen here dictates the final computational load on the node. This graph plots path loss and signal-to-noise ratio as we move a receiver across a room. The baseline curve belongs to maximum ratio combining. MRC is mathematically optimal, weighing signals perfectly, but it forces the node to continuously estimate the exact signal-to-noise ratio on every individual branch, demanding heavy, nonstop computation. Select Best Combining attempts to simplify this by routing only the single strongest branch to the output. Yet, to find that highest value, the processor still has to run the full estimation logic across the entire array. Equal gain combining bypasses this entirely. EGC simply applies a constant weight summation to all branches. It runs zero dynamic channel estimation logic, yet its performance curve sits just decibels away from the computationally punishing MRC. The SOR lens provides high optical gain, but it sits over a single detector with an area of just 3.53 square millimeters. The CDR utilizes multiple branches with photodetectors nearly 3 times that size, resulting in a much larger total collection area. This physical advantage allows the static CDR to maintain a 10 decibel path loss lead over the mechanically steered SOR, demonstrating that geometric area is more effective than adaptive processing for power-limited nodes. With spatial capture and combination locked in, we turn to temporal encoding. The modulation scheme defines the exact signal-to-noise ratio required to hit our target bit error rate. There is a strict dichotomy at the physical layer, mapped clearly on this scatter plot. Optimizing an encoding scheme for spectral bandwidth efficiency strictly degrades its power efficiency, and vice versa. Take MPAM, or Pulse Amplitude Modulation. By encoding data across varying levels of signal intensity, increasing the amplitude states pushes the scheme far to the right, maximizing spectral efficiency. But the mathematical cost of this is steep. Distinguishing between tight, stacked amplitude levels in a noisy room requires an aggressive, highly inefficient scaling of the transmitted power. Conversely, LPPM, Pulse Position Modulation, distributes energy across discrete time slots rather than amplitude levels. This trajectory maps high on the power efficiency axis. By increasing the parameter L, we stretch the signal out in time. Doing so actively decreases the required signal-to-noise ratio to hit our target error rate, making the transmission highly power efficient. For low bitrate sensor networks operating indoors, bandwidth is abundant, but battery power is strictly capped. Under these physical constraints, block time slot encoding like LPPM or basic on-off keying is the only mathematically viable choice. Modeling these highly constrained networks down to the level of individual photons reveals a consistent result. The power and compute cycles required to run adaptive steering and complex estimation logic often outweigh the signal improvements they offer. Instead, fixed spatial geometry, engineered through a conventional angle diversity receiver, outright outperforms the mechanical overhead of actively steered arrays. Constant weight addition through equal gain combining matches the fidelity of computationally heavy channel estimation algorithms without drawing the processor power. And when this streamlined spatial architecture is paired with block time slot encoding like LPPM, the system can reliably extract a pristine data stream from well below the ambient noise floor. Maximum reliability in diffuse optical sensor networks is not achieved by forcing the microcontroller to work harder. It is achieved by stripping complex processing logic out of the software and embedding the intelligence directly into optimized static geometry and strict temporal encoding.